And I'm very excited to introduce Dr. Carol Stoker, who's a planetary scientist from NASA Ames, and also an original member of the Mars Underground, which is how our society originated. And I was very happy to have been a part of a very special science expedition with her in, I think, 2011, where we went to Australia to study 3.5 billion-year-old stromatolites in the field. And it was also a very exciting occasion because it was the first expedition where Chris McKay, who was my supervisor at the time at NASA, and Carol Stoker were both on the same science expedition together, so that was a really phenomenal event. Please welcome Dr. Carol Stoker.
Okay, so I'm in the unusual position of having to be the buzzkill here. Unusual for me. So I'm going to talk to you about, why we should search for Martian life before we send humans. And given the kind of pace that SpaceX is operating at, we better start thinking about this more seriously than we have been for many, many decades. So the only time we ever looked for life on Mars was more than 40 years ago, and it was the Viking Landers that were sent to Mars in 1976. There were two identical landers. This is the young Carl Sagan standing in front of the Viking Lander. This is how long ago it was. There was two landers. One was landed at mid-latitudes, the other at a high-latitude site, relatively high-latitude site. The landers were sort of operating under the Llewellian fantasy that it was going to be easy to find life on Mars. There were 3 life detection instruments based on sort of the best technology available in the early 1970s. There was an organic analysis instrument that is actually similar, a previous generation to the organic analysis instrument that has just finally found organics on Mars. And there was a robotic arm that scooped soil into the life detection and organic analysis instruments. This is the kind of a very, this is literally out of the, the level of, sorry, the level of illustration that was available in the 1970s to show your hardware. So basically, the 3 biology life detection instruments were trying to culture microbes. They had 3 different kind of mechanisms for determining if they were detecting metabolism, but they basically were taking organic soup and or just water or water vapor and dropping it into Mars soil and then looking for what happened. So what gases were given off. The results were that the soil was unexpectedly reactive. The reactions were somewhat like Earth life would produce, but different in detail. And very much like my colleague here that gave the first talk, I was just starting graduate school when this results came in. And I read the results, and that actually sounds like they detected life. That was my reaction, just reading what their hypothesis was, how they were testing it, and what they found. But the finding was ultimately rejected as a life finding because the organic analysis showed that there was no organics in the soil. Ironically, one of these 3 instruments, the labeled release instrument, the PI of that instrument to this day believes he detected life. And I've seen him at a Mars Society convention making his case. So we learned actually 30 years after Viking that non-detection of organics was a false negative. It was produced by an unusual compound in the soil that wasn't discovered until much later. When it was discovered was the 2008 Phoenix Mars lander, which landed in a habitable zone on Mars. It landed in the ice-rich terrain at 68 degrees north. This is the only time we have ever sampled a region where life was possible on the basis of there being enough water available. This is a top-down or sort of North Pole looking down view of Mars, and it shows the water equivalent hydrogen abundance in the northern hemisphere. And the star here is where the Phoenix mission landed, and this is to the left here. This is a picture of the payload of the Phoenix lander. So basically, Phoenix was sampling a special region of Mars. The objectives of the mission were to search for a habitable environment, to search for organic carbon, and to measure the chemistry of the Martian soil. It's probably its most important finding from the point of view of understanding the habitability of Mars and why we were getting false negatives of never finding any organics on the surface of Mars, was the discovery that the soil is 1%, or order of 1% perchlorate. This is a unusual compound. It is actually found on Earth, but in very tiny abundances compared to Mars, typically. So why is perchlorate important? Well, it burns organic carbon. When you heat it up in the presence of organic carbon, it produces carbon dioxide. It oxidizes the organic carbon to carbon dioxide. And this was actually observed on Viking, but was misinterpreted. It's food. So many microbes can use perchlorate to accomplish metabolism. And it's antifreeze. It can lower the freezing point of water to typical temperatures in the Mars polar region today. So I was the lead for the Biological Potential Science Working Group on the Phoenix mission, and that was sort of a group that merged all the results from the Phoenix mission to evaluate, was the environment habitable. And our conclusion was that the environment is in fact habitable if you warm it up. So basically, there's water. It's water ice. It's right next to the surface. This white stuff here is water ice that was revealed in the very first scraping of the soil by the robotic arm. There's other evidence that the water goes through a freeze-thaw kind of process. The fact that there's patchy white ice, which actually has to be pure ice in order for you to see it at all, is a signature that the water is concentrating in certain areas caused by freeze-thaw processes. There's minerals such as calcite that are formed only in the presence of liquid water. The perchlorate itself is in patches, which suggests that it's being moved around by water mobilization. There is an available energy source. As I mentioned, perchlorate itself is an available energy source. There's also sunlight itself. If you have liquid water available, sunlight can provide the energy source for metabolism. But the high UV on Mars suggests that you have to live with some radiation protection, some UV protection. And in fact, the microscope on Phoenix found transparent grains in the soil. So there is a place to hide. All you have to do is get under a transparent grain. There are endolithic organisms on Earth that use exactly that lifestyle. And then finally, the pH was a benign kind of value, so that the environment is benign. But you have to warm it up. And, but the reality is that Mars right now, the polar regions of Mars, the icy regions of Mars, are actually in an ice age. And the obliquity of Mars varies dramatically over time, and it varies between 0 and like 90 degrees. The average obliquity of Mars is 45 degrees. But currently, we're at 23 degrees. So basically, the idea here is that the icy regions of Mars, the North Pole and the low elevation regions, because they're low elevation, liquid water can be stable if you can warm the ice up, or at least it can be possible. It's not stable, but it is possible. It is not possible in the high southern latitudes because the elevation is too high, and the pressure never gets high enough to allow liquid water to occur at all. The ice-rich soils then in the high northern latitudes are a potential abode for life, again, as the obliquity gets higher. The reason is that, and I will get into that a little bit later, but it's basically that you get just much more insulation at these high latitude sites. So this is a plot from a 2005 paper that showed what happens, where is liquid water possible at current obliquity and at high obliquity. So this plot shows you where it's possible at current obliquity based on temperature and pressure. So currently, liquid water would be possible between sort of 0 and 45 degrees in the northern hemisphere. It's not possible in the southern hemisphere, again, because of pressure. So in the northern hemisphere, the pressure is high enough, the temperature is high enough to allow liquid water, but there's no water source. So effectively, that area has been completely dried out. Now, there is some new evidence that there is ice deeper in some of these mid-latitude locations and pretty commonly available down to about 40 degrees latitude. So this slide shows where is liquid water possible 6 million years ago at higher obliquity. This is at 45 degrees obliquity. And what you see is that this whole region where Phoenix landed up to 65 degrees north, 68 degrees north, the whole area starts getting many days a year. So what this is color-coded how many days a year is liquid water possible in terms of temperature. So something like 50 to 100 days a year, it's warm enough to support liquid water conditions occurring. So that is why we think this region and this ground ice that's very commonly available now in the entire northern plains is actually habitable, not right now, but when obliquity gets higher. So given that there is at least a plausible case that there is extant life on Mars, or at least a place where there could be extant life on Mars, why do we care from the point of view of sending humans? Well, the fact of the matter is once humans go to Mars, they will take their biology and spread it all over the place. We are extraordinarily full of biology. We're basically big bags of biology. I mean, microbiology that's going to spread, and there really is no way to contain that. You just might as well face that fact at the start. So, do we care? So, it's actually been argued both ways. So, there was a 2017 paper in Astrobiology that argued that indigenous Martian organisms basically can be distinguished from terrestrial organisms by looking at their DNA. Well, the problem with that is that that is only true if Mars life is DNA-based. And if Mars life is DNA-based, then it probably shared a common origin with life on Earth, which is a plausible way to get life on either planet. But from a science point of view, being a scientist, I care about this kind of thing. You would never be certain whether the life you found came from Earth or it didn't, unless it really was not DNA-based and it was a completely different kind of genesis of life, which is an important finding in of itself. But even that would always be in doubt. So, from my point of view, there's actually a more important reason, and that is back contamination. So, right. So this actually illustrates some of the problem, that there are numerous examples of imported alien species posing, posing a risk to life on Earth. And you can see two examples in this, in this slide. But the risk needs to be evaluated realistically, and it really needs to be evaluated with data. So it has been argued, Bob Zubrin in fact has argued this to me, that it's low risk because Martian materials that are capable of hosting viable microbes arrive on Earth at an average rate of 10 kilograms per year. So Earth may already be contaminated with life on Mars. It's a good argument. The counter-argument is the following, and I think it's a similarly good argument, and that is that it's a very high consequence. Contamination of Earth by competitive alien species, particularly microbial alien species, if they upset the terrestrial biosphere, could be a very bad thing. So it's a high consequence. Maybe the risk is low, but the consequence is high. We should find out. So I need to speed this up a little bit. Are we doing anything about it? What about the samples collected by the 2020 rover? Well, they in fact are unlikely to provide information. They're really designed to find the fossil life. The proposed landing sites are all deliberately away from any special region where biology could be viable, deliberately because they don't want to have to sterilize the spacecraft or sterilize any part of the spacecraft. They don't want to have to worry about that, so they stay away from those regions. The other reason is that we don't actually even have a plan for returning those samples. We have notional ideas, but we do not have a plan and we do not have a schedule. SpaceX has got a schedule. It might not be a realistic schedule, but they have a schedule, and it's not the same as these samples would ever come back. So moving on here, for the last decade, since the Phoenix mission, a group of us at NASA Ames have been trying to get a discovery mission selected to go search for life back to the Phoenix landing site. The mission is called the Icebreaker Life Mission. The PI is Chris McKay. It uses the same lander as InSight. InSight will be landing on Mars. In fact, the first time we proposed this, it was the same time InSight was proposed. So unfortunately, the competitors managed to keep this proposal from getting reviewed, but it has been out there for a while. So basically, it goes back to the Phoenix landing site. It goes there because it's well characterized, and discovery by NASA standards is a low budget program. So you save a lot of money by going someplace you actually know about. And we know that it's a habitable environment. The mission uses a drilling system that it basically is the Phoenix lander, but replaces the robotic arm with a drill. Actually, it adds a drill because we still use a robotic arm. And we have a life detection payload. So this drill is a 1 meter drill. The reason for a 1 meter drill is that the depth to which the thermal influence of high obliquity goes into the Martian subsurface is roughly a meter. So this is a plot of the obliquity of Mars going back in time over the last 10 million years. Here's where we're at right now. And by the way, this really black curve here, this shows you what does it look like on Earth. The variations of obliquity on Earth and the amplitude of that signal, which is tiny compared to the variation of obliquity on Mars. But this is what causes the ice ages on Earth. So look at how the amplitude of obliquity is on Mars by comparison. So as you go back in time, you only have to get back 500,000 years, 500,000 years, to get to 33-degree obliquity. At 33-degree obliquity, the ground ice is melted down to, I guess I don't have the actual number on here, but it's like 20 centimeters. The ground ice is melted. So this is a habitable zone. You've got liquid water. At 45-degree obliquity, the habitable zone, it's not actually the liquid water melted zone, but it's the zone at which minus 20 degrees C, which means there's some liquid water available in the soil, goes down to 75 centimeters. So this is basically our habitable region. We have been not just proposing this, but we've been developing the technology and pushing it along over the last decade. We have been working with Honeybee Robotics, which is Pasadena company now, turns out. They have developed a drill that we have used in the Atacama Desert. Here it's mounted on a rover system. And it is a rotary percussive 1 meter drill. It's augering cuttings to the surface, which we capture with a robotic arm and then deposit into instruments. This is the characteristics of this drill, but we have been testing it in the Atacama, Chile in a field experiment called ARIDS over the last 3 years. And we've been drilling into a salt cemented deposit, which is, has pretty much the same compressive strength as drilling into ice-rich cemented soil. So the real development area now is figuring out what is a life detection payload that makes sense. So really, you know, going back to Viking, we were trying to measure life as it is alive, right? We're trying to measure metabolism. And that was because we really had no better methodology at that time. But searching for life is really not necessarily a search for something that's alive. At the scale of microorganisms, shape is not convincing. So the best evidence of life is really the chemistry of life, biomolecular structures. So basically, the instruments that we are planning to propose, and by the way, we're in the next proposal for discovery, which is our target. We're targeting a discovery proposal roughly 8 to 10 months from now, 9 to 10 months from now. So basically, the signatures of life we would look for are the chirality of amino acids, the pattern of large lipid or larger lipid molecules, and basically the pattern of organic carbon molecules. The science objectives of the mission are to search for biomolecular evidence of life, focusing on high molecular weight compounds uniquely produced by biology. Again, organics look for a chiral difference in amino acids. Life can choose either left or right-handed amino acids, but it has to choose one or the other. And if you find life on Mars and it has a different, has chosen a different handedness of amino acids, that actually means it is a different origin than life on Earth. If it has the same, then it might be a common origin. You search for patterns of organics not found in abiotic systems. And then from a habitability standpoint, you want to characterize the biologically available nutrients. There is another instrument that we have been focused on, going back all the way to our proposal that was submitted at the same time as InSight, and that is this instrument called the Signs of Life Detector. It's actually produced by our collaborators in Spain. And this, you might think of this as an immune system in a box. It actually uses antibodies to organic compounds that are grown up biologically. You literally do this in the skin of a mammal. And the reason that this instrument is continuing to be on board is because, number one, it's actually about the highest TRL instrument for life detection in existence. And that is because since Viking, NASA has put zero money into developing life detection instruments until 2 years ago when they put out a call for instruments to look for life in Europa. So Europa is now getting all this attention as the place to go look for life. Europa is under 30 kilometers. Liquid water on Europa is under 30 kilometers of of ice to get to water. We have now discovered a lake on Mars that's under 1 kilometer of ice. So, you know, why are we so focused on Europa and ignoring Mars? But anyway, getting back to this signs of life detector, it's also a very important instrument for determining whether there's risk to life on Earth, whether there's risk to astronauts by anything you find on Mars, because it is like a human immune system in a box. This instrument, we have been using it in the Atacama as part of our field experiments. We are able to detect biosignatures with this instrument that are found under, basically underneath soil that has been at least 1 million years sitting in the Atacama Desert completely dehydrated. So it is very relevant for searching for these biomolecules that will not be metabolizing on Mars, but could be in the soil. So let me slip to my last slide since they're warning me I'm running out of time. I'm going to channel Carl Sagan here. It's been 42 years since Viking. Isn't it time we resume the search for life on Mars? So in conclusion, prior to sending humans, we should perform a search for extant life in a habitable special region. The results will provide a new understanding of the potential for life on Mars, and it will lower the risk potential for human exploration. It could result in a historic scientific breakthrough, and it can be accomplished at modest cost through the NASA Discovery Program. However, the NASA Discovery Program is hotly competed, and it is the bar for excellence is kind of like winning the lottery and the Olympics at the same time, because you have to be very, very lucky and you have to be very, very excellent. And so it turns out that the next opportunity, the discovery opportunity for Mars, doesn't actually get data sent to the northern, basically the Phoenix landing site, until basically 2029. So if SpaceX stays on schedule, this mission will lap them by 5 years or more, you know. So maybe we need to rethink this from the point of view of human exploration. That's my
Okay, there's a lot I could say. I would point out that, just parenthetically, that the refutation of the argument that DNA sequencing could be used to show that the life found on Mars was not from Earth, that it wouldn't work if the organism doesn't use DNA, is quite absurd, because if the organism doesn't use DNA, it didn't come from Earth, okay? But putting that aside, why would you imagine that there would be any confusion that if you found biomarkers underground on Mars, as you're looking for in your Icebreaker mission, that were generated millions of years ago, essentially fossils, as it were, that there would be any confusion that we didn't bring them? I mean, if they were there 1 million years ago, how could we have brought them?
Yes, if you do that search before you spread human biology or human sourced biology all over the surface of Mars. So, you know, the Mars is actually more habitable than we have been thinking since Viking. And I think it's extremely likely that you know, independent life will start growing up. I mean, it won't just be You just cannot clean human activities well enough. So yes, you could conceivably, you could go to a place that's far enough away and you can drill into, you can go into the Lake Vostok that's now been found in the southern, near the South Pole of Mars, and do an independent analysis. That's true. As I said, I think the far greater risk is actually the risk of returning humans to Earth that have been on Mars until we have a better understanding of what's there now. So yes, these are fossils, but that doesn't mean they can't be woken up. They're not really fossils. They are dormant, if they're there. And we don't know if they're there, but if they're there, they're dormant microorganisms. But I think you and I should have an offline discussion about this because this could go on for a long time. Yeah.
Hi. Thank you for bringing up the old Viking data because I've been wondering about that quite a bit. And it kind of, it can also extend to what Zubrin was trying to ask. You forgot to mention the resistance of the scientific community sometimes to accept what would otherwise be difficult to accept information, like that the first Viking data showed the possibility of life. I know it was rejected then. It seems to me, because I was glued to the newspaper during that time, because that's how we got our information, that there was also when the soil was first put into the container, it seemed to outgas something, and they weren't sure what it was. One possibility was water. And now, of course, we see, like, I think it was the Pathfinder balloons that from it landing, it had mud on the surface of the... so I was wondering if, am I remembering correctly, and if I did, if there's a number that we can pull out of that that could possibly be useful data to consider.
Well, my own opinion is that the Viking Landers very likely did not detect life because they were in not inhabitable regions. I think you need to be in proximity to the ground ice because you need to have a source of water. The Viking 2 actually might have been in that region. It was at like 50 degrees north. But, at this point, so one of the problems with the entire technology of doing metabolism experiments is that we now on Earth know that metabolism you cannot grow up from almost any extreme environment. There's only something like 1% of the bacteria in the environment can actually be cultured, which is what we were trying to do on Mars. But at the time, culturing was the only way we had to study microbiology. We had no other methods.
Yes, it was that other piece of there might have been some outgassing that they had to, so when they put a soil sample in order to do the experiments, they had to like heat it up, get this out of the way, whatever it was. And nobody would accept at the time that it might be water because it couldn't possibly be on the surface. But now we're seeing that it might be.
Where would you rather be, you yourself, hiking around Mars, picking up interesting rocks, breaking them open, or where would you rather be, here on Earth, analyzing data sent back by robots? Where would you rather be?
Is that a trick question? So if I were younger, I would say I would much rather be on Mars doing it. But I don't think that this is I think it's a false dichotomy. All I'm saying is that it is prudent to search for life on Mars with a relatively simple spacecraft that does it robotically. And it is more prudent to do that than to decide that there is no risk to Earth and we're just going to go to Mars with people and then we'll look for life. It's simply prudent. Obviously, I haven't convinced you.
Okay, last question. Harold?
Hi, on your right. Thank you. If the potential location for life on Mars is inside the water ice, couldn't we completely eliminate any risk of contamination with our internal systems and humanity on Mars with a simple filtering system like reverse osmosis? Wouldn't that eliminate any molecule other than H2O coming from water ice on Mars?
So you're asking, can we just filter out terrestrial biology from all of our systems?
So if the risk is going to Mars, using the ice, picking up a microbe and bringing it back to Earth, couldn't we completely neutralize that risk by just filtering the ice before we utilize it?
It's not the ice or the samples, or it's the fact that you are a big host system yourself. The astronauts and all of their systems. There's no way to come back to bring people back from Mars without bringing back Martian materials and Martian contamination. There's just no way to do it. On the moon, I mean, this was recognized during Apollo, and the astronauts were kind of kept in a cage or something after they returned from the moon as a precaution. But, you know, it was kind of a silly precaution. This is, again, you know, if you want to do one-way missions to Mars with astronauts, fine. That's perfectly acceptable. It's, but I think it is prudent to understand more about the possibility of life on Mars. And I'm not saying it's there. I'm just saying there are habitable environments, and there are climate cycles that make Mars in a particularly poor habitability state right now. It is prudent to have better information about the existence of life on Mars than we have now before we send people.